Hello again, this is Dr. David Riley, and there's me. This is a special mini lecture just to cover longitudinal surveys. It may be quite unlikely that there are any students employing longitudinal surveys, but if you are interested in this type of design, or perhaps you're interested in evaluating existing literature that employs longitudinal design, there are some special ways to actually demonstrate causation. So this next video is entirely optional and would only be useful if you were considering employing a longitudinal survey and those issues of causation. So longitudinal surveys across 2 time points are actually common. But what we're talking about in this lecture is a special type of design that would involve multiple time points. It's entirely optional, and it may be that no student watches it, but I've spliced together a previously recorded lecture on the subject for those with a special interest in this type of design. With careful use of regression and correlation, it actually is possible to, if not prove, then certainly bolster the evidence for causality in survey research. So without further ado, I'll move on to the previously recorded lecture.
Okay, so longitudinal survey design and analysis. So we're going to go through this topic of causality, then the research designs, and then the analysis. So a fundamental point of difference between this and what you've done in previous courses is that we're not actually going and experimentally manipulating the independent variable with the survey. We're not delivering an intervention or a treatment to test for an effect on the dependent variable. So what we've done is we've sacrificed a lot of that internal validity, that control over everything, and instead we're investigating naturalistic groups. So, for example, we don't assign participants to groups. We measure their gender, but we don't say you'll be in the male group, you'll be in the female group. We just measure, are you male, or are you female, or are you some other category? Instead, we're measuring existing traits. So these are typically continuous variables. Like in your assignment when you perhaps measured extroversion or openness or agreeableness or maybe conservatism, and you saw whether this predicted the outcome. Sometimes too, though, we will look at a categorical variable, which we dummy code for, like gender, or like whether you believe it's appropriate for people to use emoji in business and things like that. And then we can look at association. So because we've sacrificed that internal validity, that makes it very difficult, but not entirely impossible, to establish causation. So just a refresher, remember the determinants of causation are based on 3 criteria, which we covered in the week 2 lecture. The first is the constructs need to co-vary. So as one construct goes up, your predictor, so too does your dependent variable. Or perhaps as your construct goes up, your dependent variable goes down in the case of a negative association. There must be temporal precedence, and this is a term that we'll be referring to again and again in longitudinal designs. So the IV precedes the DV. We also need to rule out any confounding factors. So there are alternative explanations that need to be ruled out. So, for example, a spurious correlation, the existence of a third variable that explains the causality. All right, so temporal precedence is something that a little bit hard to get your head around. It's basically that one event precedes the other. So we often refer to this as the domino effect. One event causes the other. So using the analogy there, some dominoes, you see how each domino tips over, but the next one doesn't start moving until it's been touched by the preceding domino. That's why we call it the domino effect. So you can establish that there's actually a causality there. One precedes the other. And then we need to head off those counter-arguments of potential confounds. So things like maturation, which you would have in a developmental study with children, history effects, regression to the mean, all those lovely concepts you covered in 1003. Sometimes, too, you've got an extraneous variable, and you might actually want to measure that variable. So if we predict that socioeconomic status is affecting the outcome, well, we might measure that, show that the correlation is non-existent, and then we've ruled out that third variable. All right, so that's how we establish causation. So in survey-based research, just the statistical tests alone won't be sufficient. You need to cover a lot of these principles in your design. So we can use statistical tests to see if two variables of interest are associated or correlated. And that will meet our covariate assumption. The other thing we can do is consider confounding factors. So they can be limited by including extra predictor variables in the regression analysis. So if you have something, I'll give you an example. The example from way back in probably week 2, where we were looking at the correlation between the weather and acts of... No, it was between ice cream sales and acts of violence. Our confound there was the weather and the temperature. So if we wanted to rule out temperature as a confound, we could measure temperature and see whether that also predicted the outcome. So sometimes you throw in variables just ahead of time, anticipating a potential argument against your research, and you throw them in to show that they're not correlated. So you measure the potential confound not because you expect that they will predict, but to statistically control for their effect. So that gets rid of the confounds. The problem, though, is this temporal precedence. That's actually a lot harder to test because you can measure two events, and if you're measuring them at the same time, you can't establish temporal precedence. So often you need to reach back further in time and measure something ahead of time and then see whether it predicts an outcome in the future. So in cross-sectional research, temporal precedence can never be directly empirically tested. The causal direction is actually inferred by allocating a variable as the criterion, the dependent variable, and the other variables as predictors. This suggests that the IVs cause the DV. But we can't prove that because there's also the possibility that the DV causes the IV or that some third variable affects it. So what we do is we use theory and previous empirical findings to actually justify this causal direction. So in your assignments, when you were looking at attitudes to people's attitudes to emoji, what you did was you measured some predictor variables. You didn't just hypothesize there's an association and then run it. You actually came up with a justification for the hypothesis. You looked at previous literature, you cited previous studies, so past findings. You might have cited general psychological literature, so for extroversion. You might have cited literature that extroverts are more verbally expressive, that they enjoy novelty, and so therefore they may be more likely to adopt a new form of communication and be less inhibited about using pictures for communication, something like that. So you can justify it with previous psychological theory or with previous studies that have found a similar effect. That bolsters your evidence for a causal direction. Doesn't prove it, but it does bolster it. So in some instances, it's actually quite impossible for one variable to precede the other. So for some variables like age and height, we know that as children get older, their height increases. Being tall doesn't grow your age. So if we increase their height, hypothetically, put them on the rack, stretch them out, that doesn't make them instantly age. So it's impossible for the height of the child to cause the child to age, hence temporal precedence is fairly easy to determine. It's intuitive. One thing you can do, though, is use very clever wording to help boost an argument for temporal precedence. One way would be to use retrospective measures. So I ask you a scale or a questionnaire asking about events in the recent past, or perhaps even the distant past, and we see whether they correlate with your current attitude or your current behaviour. So suppose that research question was negative interactions with out-groups. So you've all done social psychology, you know that in-groups are preferred, out-groups are, we're more prejudiced, more discriminative towards them. So if we've had some negative interactions with out-groups, well, that will probably increase our level of prejudice. Because we had bad experiences, they confirm our expectations. They're not like us, they're different. So we might hypothesise that they're positively correlated with prejudice. So we could ask participants, well, in the last year, how many interactions have you had with this particular out-group, and have they been negative? Have you got into arguments? Have you been cut off on the road by someone from that out-group? And you could imagine that someone who is prejudiced, it would fuel their beliefs that they're different, they're separate, they're not like us. And then you could actually look at the correlation and see whether it's related to their current level of prejudice. So that might be one way to sort of bolster evidence. You can't rule out third variables, but it at least sort of supports your course of direction. There are limitations, though, to this sort of approach. One is that there'll be a strong level of recall bias. So memory can be very unreliable, especially about distant events. So if I were to ask Matt, what did you have for breakfast? Can you at least remember? You don't have to tell me, but you can remember what it was? Can you remember what you had last week? This day last week? No. And then a month ago, a year ago. And there's often a bias towards recalling the more negative aspects. So we remember the bad stuff, we often tend to forget the good. So that could really affect the validity of any conclusions that you draw. It's a particularly difficult thing to do when you're studying eating research or drinking research, because people tend to forget what they ate and drank, even the last day, the last week, certainly the last month. Or there might be social desirability bias. So, no, I only had 2 drinks last week instead of 5 or 10, 15. So we downplay it. So memory can be very unreliable, and particularly about socially desirable or about distant events. So if I ask you about your early childhood, and then we match that up perhaps to your parents' reports, your siblings' reports, historical reports from your teachers, you might notice a bit of a discrepancy there. because the mind does play tricks about distant events. So it's still impossible to determine temporal precedence in those sorts of cases because we don't know what their level of prejudice would be prior to the specified time frame. So 2 years ago, 3 years ago, maybe they had some really bad experiences then, or maybe they had some really good ones that buffered them against prejudice. So that would be problematic. So we need to move further back in time if we really want to establish temporal precedence. Now, that would be a good study to do initially, but it wouldn't be sufficiently compelling that the research would stop there. So the only way to test for temporal precedence in survey-based research is with what we call a longitudinal research design. A cross-sectional study, so it would gather a group of people across a group of age groups, that only provides a snapshot of a given moment. So if I measured, for example, attitudes towards sexism today, it would be very different to if I'd done it 20 years ago. Okay, there would be more tolerance for sexism. We would disagree on the definition of sexism. Today, maybe in tomorrow, in 10 years' time, we'll have a totally different attitude. So it only controls that point of time, and we don't know about developmental effects, which are really important with children, and we don't know about historical effects. So cross-sectional research, although it's nice initially, you need to go further. A longitudinal design allows researchers to look at processes over time, how one thing leads to another. However, these designs are often within a specified time frame. So the time frame is usually the duration of the study. The temporal precedence of what occurred prior to that time frame cannot be determined. Thus, in survey studies, temporal precedence is often described as a process within a time frame. We really can't say what's going to happen after, and we really can't say what's going to happen before, but we can at least say within this time period what we think is driving the causal direction. So we're going to go through some key concepts now. One thing is the panel design. Now, so panel designs are the gold standard technique in longitudinal research. Do you all understand what that metaphor means, gold standard? It's the best, most reliable, most accurate way of conducting the study. And the reason that we say gold is we used to use for our currency. The value of our currency fluctuates, but it's guaranteed because governments have a stockpile of gold equivalent to the amount of money that they print. Of course, these days they just print more money. But in the past, that's what they used to do, and so that's where the origin of that phrase is. And you've probably heard of panel designs before. For anyone who's done developmental psychology, it's something that we do a lot because that's the only way we can test developmental effects. You've probably come across it before, but in a panel design, the same participants complete the same questionnaire or the same test over multiple time points. And then we can track their stability or their progress, their growth, across each of these time points of the panel. This ensures that both the predictor and the criterion variable are measured at multiple time points. And if you're not sure why we would measure the predictor and the criterion across multiple times, I'll show you in a moment because there's actually a logic behind it. So another two concepts that we need to be familiar with are these two terms, stability and change. So stability refers to the degree of consistency, how stable they are in their actual score, or the mean of a group, or the rank ordering of the participants from one time point to another. And change refers to the degree of fluctuation in scores, means or rank orders from one time point to another. So if we have the same score at time 1, time 2, time 3, time 4, nothing's changing. But if we find there's a correlation between time 1, time 2 and time 3 and time 4, that actually allows for our means to be increasing a bit or decreasing a bit in response to treatment or the passage of time. You've got a question? Okay, so for those playing at home, we've got a question. What's the difference between these and the concepts of reliability and validity? Well, with reliability, you're talking about a consistency in measurements either across all the individual items on a scale, or in some cases, if you have a construct that's not going to change, so like IQ, test, retest reliability. Will the test measure the same thing each time? Validity, though, is about how valid the measurement is. Not just your accuracy, but is it measuring the construct that we're interested in? Now, reliability is very similar to this concept of stability. If your construct isn't changing, and your test is reliable, then you should see stability across your time points in a panel study. But unless you have a reliable instrument, you won't know that, because it could just be fluctuations due to the instrument itself. If, however, you've got a reliable instrument and you know test-retest reliability is high, and the construct still changes, or the measurements change, then that suggests you've got this second possibility here, change. The construct is either going up, maybe your CBT is helping their level of depression, or it's going down. Maybe CBT is reducing their anxiety level. Okay, so no, I had that run the other way. You would hope that CBT would also be reducing depression. But maybe, let's say it's reading intervention and your scores and your reading test are going up and up and up. That would suggest that your reading is getting better and it's the treatment that you're delivering, or the passage of time, or the extra educational resources. So that if it's a positive. So does that sort of answer your question? You can't establish stability unless you've got reliability. So it's an important prerequisite. And if you've got change, you need to be sure that it's genuine change in the construct and not inaccurate measurement of your test. So they're important prerequisites for doing any of these panel designs. Okay, so basically these concepts are about in what ways and how much do these things stay the same over time versus how much do they change. So you often take a baseline measurement and then you retest it and retest it again and retest it again to see whether the construct is changing. Now, the direction of the association is also something you've got to consider. In life, when you've got a very, very simple relationship, it will be unidirectional. There's a clear direction in the relationship between the predictor and the criterion. So, age increases height. It's not a reciprocal relationship. But in most cases in life, you don't have that nice unidirectional relationship. Things are a bit messy. And you often have the IV influencing the DV and the DV influencing the IV. But if you're lucky enough to have a research question with a unidirectional relationship, you can actually provide really strong support for temporal precedence. Your life will be easy. But in most cases, the predictor variable is related to the criterion variable because it influences it. But the criterion variable is also related to the predictor variable. So I'll give you some examples of that and why we need to consider in a moment. One would be anxiety. So I'm just going to go back to a sort of clinical approach here, something that we can all relate to because we've done a little bit of clinical psych. We know that anxiety, because it's unpleasant, no one enjoys being anxious, you try to avoid the things that make you anxious. So it leads to this avoidance behaviour. But we know too that if you consistently avoid something that makes you scared, then your anxiety will increase. So your IV is affecting the DV, but your DV then goes on to affect your IV in the future. So you've got this bidirectional relationship. In that sort of case, it's not easy to conclude that one variable occurred prior to the other. So temporal precedence cannot be determined. Both variables sort of cause each other. Unless you've got a variable that you can go back earlier in time before the anxiety disorder and then follow it longitudinally. That's one way to sort of rule out those bidirectional relationships. So how do we go about analysing these longitudinal studies? Well, we use regression. So we'll go through 4 different types of regression here. There's Simplex model, the longitudinal correlations, the residualised longitudinal regression, and the cross-lag model. Okay. One thing that you should know when you're looking at the literature, Americans, because they're special, they spell it as residualised with a Z. So it's more commonly seen in literature. If you're ever trying to do a literature review, you need to do both spellings in order to identify it. So that's something that you need to be aware of. Now, all of these techniques, they all use statistical regression. So you've probably been exposed to, in 2000 PSY, the factorial ANOVA. So the factorial ANOVA is really good when you've got a categorical IV, so the treatment group that they're in versus a control group, or the placebo, or maybe you've got a variable like high, medium and low, so maybe extroversion, high, medium and low, or academic ability, and then you can plug that into an ANOVA. But the problem is when you take a continuous variable, like extroversion, as a personality trait, and you partition it into low, medium and high, you actually lose statistical power. So you're less likely to find the effects that you want. And so that's why we would use a regression analysis for a longitudinal study, because we can actually plug that independent variable that we measure straight into the regression model, and we have greater statistical power. So although you could analyse it using an ANOVA, and we sometimes do if we've got oodles of statistical power and lots of participants, but the problem with the longitudinal study is you've got to get people to stay in your study that might last weeks, months, years, 10 years. So you have people drop out and you lose statistical power. So you need every ounce of power that you can get, and that's why we analyse these with statistical regression instead, so that we can plug in a continuous predictor into it. So the first one here is the simplex design. It's also the most simple. It's often referred to as an autoregressive design because it involves regressing a variable onto itself across several time points. What do I mean by regressing a variable onto itself? Well, that's a nice fancy way of saying we look at the correlation between our dv at time 1 and our dv at time 2 and our dv at time 3. And we see whether there's a high correlation between that. If they're measuring the same construct and we really do have stability, then there should be a pretty strong correlation between the two. You know, as long as we've ruled out practice effects and things like that. If there's not a correlation, then that suggests that there's a lot of change going on. Something else is affecting it. So in other words, the measurement of a variable at time 1 should generally predict that variable at time 2, indicating stability. So T1 to T2 and T2 to T3, they'll all be significant, just as T3 to T4 will be significant. It'll also be a strong correlation. We're not talking 0.2, 0.3 like maybe you saw in the assignment. We're talking 0.8, 0.9. They're measuring the same construct. There'll be a little bit of sampling error, but there shouldn't be too much. So if you're measuring a variable like depression, you're not going to be bouncing up and down like a yo-yo. It'll be fairly stable, fairly consistent, unless you're delivering an intervention that improves, reduces it. So this type of model is called autoregressive, as the values of a scale are automatically regressed, autoregressive, onto the same scale. And that type of analysis allows researchers to explore the stability and change in the one construct that they're measuring. So if we measure something like depression across adolescence, do depressed kids stay depressed, or do they grow out of it generally? Pick another condition like attention deficit. Do children who get treatment with attention deficit, do they tend to have it persist across their childhood and into adulthood, or does it reduce over time? Generally it does, unless, it's undiagnosed, you don't get the educational support, etc. Okay, so we're going to have a look here at a simplex design with a picture. I find pictures make it a lot easier to understand this sort of thing. We've got a dependent I'll get out my little laser pointer. Dependent variable there, measured at time 1. And we want to see the correlation between the dv at time 2. So this is our standardised regression coefficient, or beta. And if there's absolutely no change between those constructs, then we will have a perfect autoregression. Of course, that never happens in real life, because there's often things that go on, like sampling error, you're feeling sick on that day, and so it's never completely 1, but as close to 1 as you can get, that's generally a good sign. So a perfect association between the two time points indicates that their relative standing, if they're at the top of the pack at time 1, they'll also be at the top of the pack at time 2, has not changed. The rank ordering of the participants will generally remain the same. So it's possible for their score to increase. Let's say it's a spelling test. Generally, grade 1 and grade 2 will spell better than grade 1. But if they were a good speller in grade 1, they should still be a good speller in grade 2. And if they were a bad speller or a mediocre speller, then that's what they should be at time 2 as well. So it's about this relative standing. And remember, you will never get a perfect correlation because there are things like measurement error, sampling error that can occur. Also, the longer the passage of time, the lower the autoregressive coefficient will be. So if you're talking about measuring a particular outcome every week, should be pretty consistent. But if you're measuring at an interval of every year or every 2 years, then you'll start to see lower autoregressive coefficients. So a large autoregressive coefficient can mean one of two things. Either that individuals do not change over time. So my IQ is fairly fixed. It won't go up and it won't go down, absent any, head injuries or stroke or something like that. If you have a child and you provide them with enough education, their IQ at the end of adolescence will be the same as their IQ in their 20s and 30s and 40s and 50s. Okay? But it also allows for the possibility that individuals uniformly increase or decrease over time. So if we take a mathematics test and we measure in grade 1, and then in grade 2, and then in grade 3, yes, we should see an increase. But you'll probably find that unless one group is getting a differential level of treatment, so better education, more access to teachers, that sort of thing, then they'll be consistently increasing at the same rate. So their rank order probably won't change. Now, there are other more complex and less common explanations. Fortunately, we don't have to deal with them. So there's only those two possibilities. And we're going to illustrate it. So we've got here perfect correlation. You've got it from the bottom left to the top right. Perfectly fits our regression line. And all I've done is I've taken their scores at time 1 and I've selected that column, and then I've pasted it in SPSS, and they get the same score at time 2. That will give me a perfect autoregression coefficient, because there's no change between time 1 and time 2. 2 and 2, 5 and 5, 4 and 4, we're going to have a perfect correlation. Now here's a perfect correlation where the scores do change. From 2 to 4, it went up by 2. From 5 to 7, it went up by 2. From 4 to 6, so it's increased uniformly. So we're going to get the same perfect correlation there. So when you see an autoregressive coefficient, it's only telling you about the change or stability. It's not telling you whether it's going up or whether it's going down. Just tells you if they're correlated. So it could be that they're flatlining, no change, or it could also be that they're increasing at the same rate across all participants. You need to consider both possibilities. And one of the examples that I'll show you today, to establish that, they had to go one step further and show that their means went up over time. Okay, so with simplex designs, generally you want to, depending on your research question of course, but generally you want to establish stability. So across each of these explanations, the rank order of the participants has not changed. So for this one here and that one there, the rank order didn't change. Therefore, on a between participant level or inter-individual level, there's stability. 5 becomes 5, 4 becomes 4. So if we are going to have a look at the rank order, The rank order of participant 2, they're number 1. And the rank order of participant 3, well, they're number 2. Let's have a look at another one. We don't have a high order regressive coefficient. A small or close to zero association between 2 time points indicates that the relative standings on the construct have changed, and changed pretty dramatically. So some of them went up, some of them went down. There's almost no correlation between those 2 points. Now, it's very rare you'll get a perfect one. It's very rare you'll get a zero order regressive coefficient. The truth lies generally somewhere in between. But to illustrate the concept, we've gone for the most extreme examples. So, at time 1, they got a score of 2, and at time 2, well, they went up big time, 16. But participant 2 here, they went from 5 and they stayed at 5. 4 went up to 19, 3 went down to 2, and so you can see there's been a lot of change. And so that's why we've got not a perfect zero, but we've certainly got a non-significant beta weight there for our sample. So there really is no association there. Too much change. So with a low order regressive coefficient, it indicates that a rank order change has happened. So participant 2, at time 1, well, their rank ordering there was 1. And they stayed on a 5 now. So their raw score didn't change, but they dropped pretty significantly in their rank ordering. They've gone down to 6th position. So even though your score hasn't changed, your rank order has, so that will be a lower order regressive coefficient. So this change between the individuals. So now we're going to have a look at some Venn diagrams. I know how much you love Venn diagrams. And I'm going to illustrate time 1 using the colour blue, and time 2, because I like purple, I'm going to be illustrating it with the colour purple. And what we're going to do is we're going to have a look at the overlap between these. So go back to the Venn diagram. So we haven't coloured it in yet. And the area in between where these two shapes overlap, well, that's what we call shared variance. And you've been exposed to that concept before with the regression diagram. And that indicates stability. So shared variance indicates stability. And this non-shared variance of our dependent variable, by the way, these are the dependent variables that we're talking about, these shapes. That indicates non-shared variance. So at time 1, my average was somewhere over here. At time 2, my average was somewhere over here, moved to the right, so it's increased. And the only overlap is that shared variance. So if you're having a look at that, which is bigger, the shared variance or the change? Change? Good. Okay, so over here on the left, when we have a strong autoregressive correlation, this indicates temporal stability. So there's more shared variance than there is change. On the right, we've got a weak relationship. So a very, very low autoregressive coefficient. And that indicates there's far more change than there is stability. Now, depending on your research question, that can be a good thing or a bad thing. For some, you might want to indicate there's a lot of stability. For others, if you're delivering a treatment or an intervention, then you might want to argue that there's change. And furthermore, that change is down to your independent variable or your manipulation. So, in fact, we can actually, with a longitudinal study, incorporate a little bit of experimental manipulation as well. There is that possibility. Okay, so we're going to illustrate a simplex design with an actual example. Now, I've put the paper up there. Excuse me if I'm mispronouncing these. Verhoeven and Louis, 2008. It's an example from educational psychology. So there's a lot of developmental studies with educational psychology with young children. It was looking at the development of reading comprehension, and it was a longitudinal study. And what we did was we looked at the developmental progression of verbal and language skills. So we measured things like their listening ability, their reading ability, their word decoding ability, so sounding out words, that sort of phonological skills. And another thing we measured was vocabulary. How many words do they know? And we're just going to focus on vocabulary here for the moment. And what they did was they measured children, 2,384 to be precise, from grade 1 to grade 6. And annually, they had these skills measured. And then they plotted up a diagram that showed the autoregressive coefficient from time 1 to time 2 to time 3, time 4, time 5 and time 6. So let's have a look at time 1 and time 2. So the correlation between grade 1 vocab and grade 2 vocab was 0.95, as close to 0.1 as you can get, I would think. From grade 2 to grade 3, there's a bit of a drop. And the authors attributed the reason for this because they went to an oral vocabulary test. Little Johnny, what is a pear? What is a boat? And they spoke the words or gave the definition. Then they moved to a written test. And because there was this other construct of reading ability introduced, there was a little bit of a dip, but, you know, it's still a pretty high coefficient, 0.72. And then from grades 3 to 4, 4 to 5, 5 to 6, you've got as close to 0.99, close to 1 rather, as you can get, almost a perfect correlation. So this indicates what? What would we say about our vocabulary from grades 3 to 6? Stable. Now, there's two possibilities though, because when we say it's stable, we're saying that the rank ordering is stable. We're not sure whether a grade 6 knows as much words as a grade 3 or whether they're increasing uniformly at the same rate. So they had to go one step further. And what they did, I'll show you that in a moment, what they did was they had a look here at the means. And they presented that to show that they were actually increasing. Now, to test this autoregressive coefficient, they used some modelling. They took the standardised regression coefficients and they ran what we call a goodness of fit test. We heard that term before? Chi-squared of the simplex model, hypothesising that there's stability across grades. So do we have more change than we would expect due to standard error, sampling error? So we can see here for VO, it was chi-squared was 71.81, p less than 0.001. This indicates our model fits. There really is some stability there. And you would write that as chi-squared 10 equals 71.81, and it's statistically significant. So even if you're not going to be running these tests, the reason why I've actually given you a section from the paper is you'll encounter them as you're reading in other courses. You'll encounter them as you're reading the psychological literature. And even if you don't know how to do it, you can at least read it and understand some of those stats. You won't be bamboozled by all these big numbers. and you'll know whether it's statistically significant or not. Okay, so the strong and significant associations between each grade indicates that the relative standing of the children remains the same. In other words, children with higher vocab scores in grade 1 compared to their classmates, it's always relative to their peers, had high vocabulary scores across every subsequent grade in comparison to their classmates. So based on this information alone, there were two possible explanations. One is that their vocab doesn't change. They don't learn anything at school. Education's wasted. Or that they increase uniformly. And to show that that second case had happened, they actually presented the means. And they actually ran an analysis of variance. So you remember the repeated measures analysis of variance, and if it's significant, it indicates it's increasing, or at least that it's changing across grades. So by exploring the average, you can examine group level growth. The increase in vocabulary indicates they're increasing over time, and that rules out the possibility that this high autoregressive coefficient indicates no growth. But it doesn't distinguish between the possibility that there's uniform growth or that there's intra-individual differences in growth. So Johnny might have really developed his vocabulary, whereas Sam might have sort of plateaued out. So you can still have those individual differences there. We're just looking at the group overall. So what did they write in their paper? Well, you've seen the stats, so you should be able to understand now whether their conclusion is supported or not. So for each of the variables, significant progress from one grade to the next was consistently encountered. The other thing they said was that there was stability of the individual differences. So for vocabulary here, the stability across elementary school years was quite high. In other words, our data shows that the individual differences that occur at the very beginning tends to prevail across grades. So if you can get your kid off to a good start before they start grade 1, and that's why we do now work with pre-literacy now, why we have early education, then they should be off to a good start and continue to thrive, barring any unforeseen events. So we can see here that the stats they presented are consistent with the conclusions that they draw. Now, some papers you can't always make that argument. Sometimes they make claims that aren't supported. So the reason that we show you these techniques, so you can at least have a look at the stats and see whether it's sort of semi-plausible. Okay, now the other thing we can do, aside from a simplex design, is have a look at longitudinal correlations. So longitudinal correlations examine the relationship between the IV at time 1 and the DV at time 2. A simplex design is the DV time 1 and DV at time 2. Longitudinal, we're looking at the effect of the IV now on the DV. So similar to the correlations and bivariate regression techniques in this course, only 2 variables are being analysed. So we use a Pearson's correlation here. So for the longitudinal, now this green circle actually represents the independent variable. And the purple, that's our dependent variable. And anything overlapping, well, that sort of suggests that they're associated. Can't establish causation, but it would at least be consistent with the causation. If there's no shared variance, well, our hypotheses go out the window and there's really no association. But if there is some shared variance and we can establish temporal precedence, then we can make the argument that one causes the other. So this approach does not allow any inference regarding temporal precedence, though, because although it may predict a future outcome down the track, it doesn't test the stability of our dependent variable. Now, I'm going to give you an example, a concrete example, because it makes it easier to understand this. So let's say we're looking at children and we're looking at substance use. And we want to see whether their impulse control disorders at age 12 are going to predict their impulse control disorders, their substance usage at age 16. Okay, so we take a measurement of our IV at age 12, predict into the future, make the hypothesis, wait 4 years, and we measure it and see whether one explains the other. The problem is we can't rule out the possibility that they were already druggies or alcoholics, or they were sniffing glue and paint at age 12. So it might have been a pre-existing condition. So that's the limitation of the longitudinal correlation. It's not sufficient to rule out that possibility. Or it might be the case that there's a bidirectional relationship. Maybe kids who are engaged in substance use, maybe they have poorer impulse control, and then that leads them to do more substances, and it's like a vicious circle. So longitudinal correlations isn't sufficient. But we do sometimes use it as an initial first step. So in order to establish temporal precedence, researchers can run two separate longitudinal correlations. So we measure the IV at time 1 and the DV at time 2, but we also measure the DV at time 1 and the IV at time 2. And if there's a significant relationship between IV at time 1, DV at time 2, and there's no relationship between the DV at time 1 and the IV at time 2, then we can establish temporal precedence. Now that's very confusing, that concept. So I'm going to illustrate it with some pictures. Don't panic yet if it's going in one ear and out the other and all you're hearing is blah, 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 blah. Okay? So if both analyses are significant, though, it indicates what we call a bidirectional relationship. So let's have a look at our example. Impulse control at age 12. Okay? And 4 years later, we find there's a significant correlation with our substance use. So if you have bad impulse control, I'm thinking, a parental report, teacher's report. If we go back earlier, does anyone remember the marshmallow test? Delayed gratification and impulse control. It actually predicts delinquency in substance abuse at age 16. So when I picked this example, I was actually thinking of the marshmallow one. But we're only going to measure it at age 12. Okay, so we have informant reports from parents and teachers. Do they have impulse control issues? Or a diagnosis by psychiatrists. And we also go and measure their substance use. And the reason is, at time 1, at age 12, we want to rule out the possibility that they were already hooked on drugs or paint thinners or alcohol or whatever their drug of abuse is. And we find that there is a correlation between their substance use and impulse control. Well, that suggests to me that we can't prove temporal precedence because it could be the substance use causes the impulse control disorder. And if they were using it at 12, maybe they were using it earlier, and that association between those two is significant. But if we find that their substance use at age 12 had no correlation with their impulse control issues at age 16. Well, then we've got a unidirectional relationship, and we can actually establish temporal precedence. So in this example, we've shown that impulse control issues precedes the substance use. So we weren't using drugs then, but we had an impulse control disorder. We are using drugs now, and we've still got the impulse control disorder, but it preceded, therefore, we really have established temporal precedence. So substance use isn't causing the later impulse control impairment. The weaknesses is that it doesn't account for the correlations between variables at each time points. So what am I talking about? I'm talking about these two here and these two here. And it doesn't account for the stability in the construct. So there's no indication here of the stability or change over time. Were they always druggies or did they become druggies? So that's the advantage of the simplex design, which you don't have with longitudinal correlations. Now, the combination of these limitations ensure that researchers cannot completely rule out a relationship between T1 and T2. It's just due to a cross-sectional relationship and not a causal one. There were still people who would be so pedantic they will argue that's not sufficiently compelling enough. Very annoying. So the alternative is to do something like the residualised longitudinal regression. To address those limitations, what we can do is residualise the DV. And this is done by entering the score of the DV at time 1 into our prediction of the DV at time 2. So our criterion is drug use at age 16. But our predictor variables are impulse control at age 12 and drug use at age 12. Now, we're not expecting them to really be using lots of drugs, certainly not for the majority of people. We're not expecting that the DV will correlate with it. Not completely. But it will. We can partial out. Remember your semi-partials? You partial out the stability effect. So if they weren't drug users at time 1, they're unlikely to be heavy drug users at time 2. Take that out, and then the only thing left is the contribution of the IV. So conceptually, it's a little bit harder to wrap your head around. Statistically, though, it's just a simple multiple regression with these two as your predictor. So you have the techniques to do it. With a little bit of assistance, with a YouTube video, if you had to, gun to your head, you could save yourself and save your job and do that if you were having to do a longitudinal study in the workforce. So as a result, the correlation between the DV across 2 time points is considered. So we consider the stability, and then we statistically remove it from the analysis. This allows researchers to actually predict change. So by entering the DV at time 1, then the unique variance remaining in the DV at time 2 reflects the change in the construct over time. So remember, this is just a recap. This is your simplex model. So stability and change, the overlap between the DV at 2 time points. This is your longitudinal correlation, IV in the DV at time 2. Why not combine both? And then you have your residualised longitudinal regression. So the green here is our IV. The blue is the DV at time 1 and the purple the DV at time 2. I want you to just ignore for a moment, if it's possible, the blue, and just focus on the green here. If we measured the green at age 12, and the drug use at age 16, then this bit here and that bit here would overlap. But by controlling for the pre-existing drug and alcohol usage, we've taken that out statistically, we eliminate that, and we're just looking at this area here. And that shows the change over time that is explained by the IV. And if we hadn't included the DV, we'd expect a bigger percentage of variance, and we wouldn't be accounting for the pre-existing condition of drug and alcohol usage. Because if you're already addicted, your chances of being addicted 4 years later, unfortunately, they're pretty high, without any intervention. Particularly if you take, drug and alcohol at such an early age. Okay, so I understand that's a very heady concept to get your head around. In a moment, we're going to go through an actual example of a residualised regression, but I'm going to give you a break. Yeah, I'm going to give you a break. And come back in about 5 or 10 minutes, and then we'll continue with the lesson. By the way, if anyone doesn't know who that is, that is Mark Wahlberg. He's an actor. No, I think time one. If only your questions were so easy. But it's not monkey specific. There's cats and dogs and birds. I think I might have said that just because I wanted to do a study that. So any animal, we find that research suggests you're more likely to remember if there was a colourful image or an animal.
Can I also ask, because earlier in the slides, correlations, does it
Sometimes you can have negative associations between your IV and your DV. So IV, let's say your.
I just thought for one of them.
Yeah. Let me have a look. Pause this. All right, we might make a start again. One thing, I did have a question from someone in the break, and just so that I'm consistent and sharing the same information with everyone, they'd asked whether there was any significance to the monkeys as opposed to any of the other animals. So no, the only significance is I happen to like monkeys, and so that's why there's lots of monkeys. But I also love animals and birds and cats and dogs. Now, anytime I have put an image of an animal, that is a mental cue, and I'm hoping that you will remember it either for the exam or for a future subject or for when you go on to do honours. So any important learning outcome, if I wanted to draw attention to it, I would put an animal in the lecture slides. It's not just a whimsical element of my personality. Research suggests that adding animals reduces statistics anxiety. It increases the likelihood of you remembering that point or concept. And so there is a method to my madness. It's because I really want you to remember it. So you're not guaranteed that every animal slide that's going to be assessed in the exam, but you are guaranteed it's an important learning outcome and that you need to know it, either for this course, future courses, or for your honours, or if you go and you do a bit of survey design in your future job, because, you know, the employment options for 3-year psych graduates are actually very broad and diverse, and a lot of people do go into surveys, either for the government or for agencies or community organisations or for marketing research. So having these skills, it's an important thing. You don't just forget these messages and throw them away. Hopefully you'll be able to take it into your employment, and it gives you a marketable job skill. So that's why there'll be animals scattered here and there. Okay, so we're going to give you an example of religialized regression. So this example comes from one of our PhD students, Alex O'Donnell, and one of our former deans, Bonnie Barber, and they were looking at young high school children in grades 9 and 10 from memory, and they looked at 374 kids, and they were following their level of psychosocial well-being. So their psychosocial well-being is, you know, the level of depression, anxiety, stress. Do they feel positive about themselves? Do they have low self-esteem? Those sorts of things are all tied up in this sort of nebulous construct of well-being. Okay? And what they were investigating, and I'll get my little friend the laser pointer, what they were investigating was whether having a connection to the community, so things like extracurricular activities, social inclusion, feeling like they belonged to the community and they had a purpose, whether that actually predicted their level of well-being. And so if I did a simplex design, I could take links to well-being and then a year later measure their well-being, and I could say, oh, there is an association. But I still couldn't establish temporal precedence, even though it was predicting into the future, because we'd have to eliminate a hypothesis. And that hypothesis, our rival hypothesis, is that children with good well-being stay good, and the people in our sample, they might already have had that level of well-being. And it's got nothing to do with links to the community. In fact, maybe if you have good psychosocial well-being, you're capable of having links to the community. You feel like doing extracurricular activities. And it's this well-being that explains the later relationship, not our IV. And so what they did was they measured these both concurrently in grade 9. They then popped it into a regression equation, and then they looked at whether there's a significant correlation between community and well-being even after we control for their base level of well-being. So we're going to partial out their grade 9 well-being and see how much change in their well-being is explained by their links to community. All right, so based on previous literature, we know that well-being is a fairly stable construct. So if you're feeling great about yourself, grade 9, you're probably feeling pretty good about yourself, grade 10. Maybe not quite as good, but, you know, you're still doing okay. And if you're feeling really low and down and, you know, life is just an endless ordeal, you know, the stresses and the traumas of being a teenager, you're probably still going to be feeling that way in a year's time. Now, unless something magical has happened and you suddenly climbed in social status and everything goes well and you don't have to worry about your exams now, you know, you're still going to be really feeling pretty low. So there's a strong correlation there. We also know, but because we do our literature review before we design our experiment, we know that there's a cross-sectional contemporaneous relationship between these two constructs. So if you have links to community, you have good well-being. If you have good well-being, you tend to have strong links to community. So positive association there. So theoretically, feeling connected to the community then, it should cause higher well-being over time. So we take our links to community, we see there's a significant association. That's our prerequisite. And the stability of well-being indicates that it shares the same statistical variance over time. But the cross-sectional relationship between the IV and the DV indicates that feeling connected to the community also shares variance with well-being. What we don't know yet is what's going to happen where we control for the base level, the baseline of well-being. So how do we know that feeling connected with the community predicts a change in well-being and not, rather, the effects of stability? So by controlling for the previous year's well-being, that infers that feeling connected with the community predicts the change in adolescents' well-being. So we've got our beta weight here. This is the unstandardised regression coefficient. And, but I have a feeling actually that it might have been the standardised beta. We can see here a strong correlation here between well-being at time 1 and time 2, but even after controlling for that, we can still see there's a significant correlation between links to community and well-being. So by controlling for well-being at time 1, the stability in the construct has been removed, and as a result, the only thing that's left, links to community, actually predicts any change in well-being. And because it's a positive coefficient and not a negative one, we know that it actually improved their level of well-being. Now, if it was a negative, then we'd be really worried. These extracurricular activities are lowering their well-being. Okay, so same diagram as before, but what I've done is instead of saying IV here, DV, T2, DV1, I've actually put in the names of the constructs. And I think that makes it a whole lot easier to understand this diagram now. Rather than dealing with abstract terms like IV, DV, links to community, there's some shared variance with our well-being at time 2, so all of this part here. But when we control for the baseline level and we partial that out, the only thing that's left is our change. Yes, up the back. So in SPSS, if you go to the correlate, you'd go to the partial correlation menu option. But in a regression equation, if you did it as a regression, you'd be looking at your semi-partials. So the question, by the way, for those playing at home was, would you use your part or your semi-partials? So if you're using the graphical user interface, SPSS calls it partial, but in the regression analysis, we're looking at the SR squared, so this what SPSS calls part. And so your semi-partial is unique variance explained by links to community after controlling for the baseline level of well-being. All right. So, oh, look, there's a bird. Maybe this is important. Now that you know the trick, you know that I put it on a lot of slides, even if it's not examinable. So the trick is out there. But the correlations between T1 are statistically controlled for. The stability of the dependent variable is also accounted for, so that's a real strength. Consequently, this analytical technique allows a researcher to predict change. In other words, to actually find a longitudinal effect. And if you don't have longitudinal data, like Mark Wahlberg said in the meme there, you shouldn't be making causal attributions. That's why when in your 1003 assignment you said that the IV caused the DV, we put a big red X and say correlation is not equal to causation. But if we do this longitudinal type of study, we can actually bolster some real evidence in support of that argument. The weaknesses. Well, one is that temporal precedence is still not entirely identifiable because there's no test yet for what we call a bidirectional relationship. Did the IV of extracurricular activities at time 1 also be explained by their well-being at time 1? So you've got a few possibilities you need to rule out. So maybe you had good community relationships because you already had high psychosocial well-being and lower well-being. Well, that was actually a barrier. So your DV at time 1 actually explains your IV at time 2, or over the course of a year, and then your final DV. But there is a way to at least identify that, and that's where you have what we call a cross-lagged model. In a cross-lagged model, and this is the reason why I said at the beginning, we'll often measure the IV at 2 time points as well. In a cross-lag model, the measures serve both as the IV and the DV. So in this analysis, there's actually more than one DV. And so we haven't shown you any statistical analyses, either in 1003 or 2000 or in this course, that analyse multiple dependent variables. You get to learn about that in honours year. If you go on to it, it's not entirely fun, but it is manageable. But we didn't introduce it at the undergraduate level. But there are actually statistical tests that can handle multiple DVs. So you should at least understand the concept and this term cross-lagged. So we've got our DV here, measuring the DV at time 2. We've got our IV correlating with the DV at time 2. But also we've got our IV correlating with the IV at time 2. So it gets a little bit sort of head trippy. So in a cross-lag model, we're combining 2 residualised longitudinal regressions into the same analyses. Thus, stability of the construct is statistically removed, so all the advantages of before, allowing each variable to predict the change in the other variable. And this technique allows you to investigate the possibility that it's actually a bidirectional relationship. Now, there are 6 parameters to a 2-wave cross-legged model. Firstly, you have the correlations between the variables at time 1 and the other variable at time 1. Then you have the correlations between the variable at time 2 and the other variable at time 2. We test for stability. So variable 1 at time 1 correlated with variable 1 at time 2, and the same for the other variable, the IV. So time 1 and time 2. So that's your 4. Here comes, I think that should be 5 and 6. Sorry, my bad. The cross-lag path is the correlation between the DV, time 1 and time 2, controlling for the IV. And you also have the cross-lag path controlling for the DV at time 1 and the IV at time 1. And then we've partial out the effect of, baseline effect of the IV. And so we're just looking at the change in the IV at time 2 explained by the DV at time 1. So the well-being at time 1, whether it explains the links to community at time 2. So you'd add this cross-lag design after you've gone and done the initial study, shown that there's some degree of temporal precedence support, and then you'd go one step further with a new study and you'd rule out the possibility that it's a bidirectional relationship. So let's have a look at a cross-lag model. And this is taken, if you're curious, from Gunson and Bulens. I'm probably horribly mispronouncing these. It was 1,006 adolescents measured over a 2-year time period. And the analysis investigated the longitudinal relationship between binge drinking, so drinking to an excess, and this construct here, which was a rather novel one, sharing alcohol content on social networking services. So what type of content are we talking about? Well, maybe you share a funny beer commercial, the Budweiser ads. Maybe you share a picture of yourself dancing on the table drunk. Maybe you share a picture of your mate spewing into the gutter, drunk. Maybe you have a selfie photo with you and the Bundy Bear, or maybe you show a picture of all these empty alcohol bottles of spirits at the end of the weekend. And the idea being that there's some sort of relationship. Now, does binge drinking cause you to share alcohol content, or does the alcohol content, that the type of person who would do that and think that this is a good thing to be sharing, not just amongst my peers, my parents, my family, my future employers, maybe they're special in some way and they're more susceptible to binge drinking. So what's driving the relationship? Is it unidirectional or bidirectional? Okay, the model investigated the direction of the relationship between sharing alcohol content and the binge drinking. If one of these variables predicts change in the other over time, then we have a unidirectional relationship. But if both variables predict each other, that tells us we've got a bidirectional relationship. And without temporal precedence, it's impossible to make a conclusion regarding causality. Does sharing alcohol content on the Facebook or Instagram, does that lead you to be more susceptible to binge drinking? So in this example here, this was actually taken from the paper. We've got our beta weights here. You can see there's a significant relationship between the DV and the IV, and the IV and the DV. So that would suggest a bidirectional relationship. But this one would suggest a unidirectional relationship. Okay, sharing alcohol content predicts your later binge drinking, but binge drinking doesn't predict your likelihood of sharing alcoholic content. So our beta weight here is non-significant. It's really tiny. So that tells me that we've got a unidirectional relationship. And, you know, if you get a diagram like that, even if the author doesn't state it, you should be able to identify, well, hold on, this might be a unidirectional or might be a bidirectional. Maybe they're conclusions I need to interpret with a little bit of caution. So I'm not expecting you to actually do these analyses, but I would expect you could interpret this type of diagram either in an exam or a journal article in a future course, or maybe you're reading some psychological literature and you can say, well, yeah, it looks like it's only a unidirectional relationship, or it looks like it's a bidirectional. Okay, so as long as you know what the concept is, that should be sufficient to prepare you for future courses and future learning. Okay, so we've got an overview here of regression, longitudinal regression, and what I've done is I've done a checkbox. Which things estimate stability and change? So you see here the longitudinal correlation. It doesn't deal with stability and change. It only explores unidirectional relationships. Whereas the residualized regression, it handles all of those. And that's great as long as you don't have a bidirectional. Because if you have a bidirectional, then you need to use a cross-lag model. But of course that's more expensive, more measurements, more work. And so often, if you know the literature suggests it's unidirectional, you can get away with a residualized regression when you're planning it. So you always consult the literature. You know, you don't try to reinvent the wheel, but it's important that you at least have an understanding of the limitations of these techniques. Okay, so I'm just going to go through very quickly the assumptions. Inter-individual stability. This examines stability and change. It's assumed that there's no systematic differences. You know, one group of participants didn't differ in some way to the others in the type of stability and change. That assumption is violated when one group of participants changes faster or slower relative to the other participants. You know, maybe males develop more slowly than females. Educationally, that's the case. So that assumption may not be tenable for some certain studies, depending on your research question. Consistent measurement. Now, we have the same amount of time in the interval between our measurements. We don't do 1 weekly measurements, then a yearly, and then back to 1 weekly. So in practical terms, that means that the items administered to participants need to be exactly the same across time periods, using the same measures or at least consistent measures. In conceptual terms, participants need to read and interpret the questions in exactly the same way across time periods. So developmentally appropriate questions for grade 6 would be different to developmentally appropriate for year 1, but then you've changed the wording, so maybe you've got some problems here. So if you're not having consistent measurement either in the time interval or in the type of measure, then that is a threat to your validity. Synchronicity. It's assumed that the administrative of questionnaires occurs with the same interval between time periods for all participants. So don't ask some in a month's time and some in 3 months' time, because historical events might change the outcome. Maturation might be a threat, so you ask them all at the same time. Synchronicity. And the time frame, in order to find a longitudinal effect, the length of time between measurements needs to be considered. The time frame may simply just be too short to impact another, and so you won't find an effect. So if I'm giving you some therapy with CBT and I want to see your effect of the change in depression, if I do it 1 week intervals, maybe for 2 or 3 weeks, probably not going to be sufficient to demonstrate lasting change, and therapy may actually make you worse initially and then have a long-term benefit. So you want to consider the interval for your time frame. But if you do it too long, then the longer you do it, the lower the autoregressive coefficient is going to be. So if you think about some studies, I'll give you an example. NAPLAN. You might not have thought of this as a study, but it is. The government uses it to track school data, trends in educational improvement over time. So we measure children in grades 3 and then 5 and then 7 and then 9. So we would expect lower correlations between 3 and 5, 5 and 7, 7 and 9, than if we were to do the test annually or perhaps 6 monthly. So there's a price that you pay for measuring more often, and that's cost. But if you space out the interval too long, you're going to have lower correlations. So when you're planning your design of your experiment or your study or your intervention, you need to consider that. If the time frame is too long, then the impact of one variable on the other may have dissipated. The other thing, and this is a really serious threat, is there might be a third variable, a spurious variable. Like in the ice cream example, there was, you might find temporal stability, that ice creams consistently predict violence, but there's a third variable like temperature you haven't controlled for. So you need to consult your literature. If you identify something that, or someone makes a claim that your study could be explained by this third variable, that's an easy solution. Just measure it. Include it in your regression analysis. Show that it's not correlated. Problem solved. So you plan ahead and you identify potential third variables, and then if you are doing a longitudinal study, add it and then control for it, and you should be right.